not very favorable. So, well, let's see if they can connect a little bit later. Any case, thanks for the invitation, Ignacy, and it's a pleasure to give this talk. It's a work related to our research line on additive manufacturing, and this time the topic is about polymer-based material. So, as you know, well, as you probably know, we had and we still have different projects on metal additive manufacturing technology, but in the latest years, we had the possibility to work on this new technology for additive manufacturing using polymers. And well, one second. Okay. No avanza la presentación.
Maybe you can try stop presenting and doing it again.
Oh.
It's working now.
So this is the research team at CIMNE. The truth is that we start working with the Comet group, meaning myself, Narges, Miguel, Carlos, and some of the PhD students, Marta, Carlos, Kim, Ivan, which is the new arrival. Then things get a little bit more difficult, so we needed the help of Ricardo from the Kratos group. I will tell you which is his involvement in this work. And finally, we have some new idea on new developments, and so we will probably need the help of Joan, Ramon, and the Git group to move forward in this work. And the idea is to be able to study, to perform numerical simulation of CIMNE components made by polymers. There are different kinds of polymers, PA, PLA, there are ABS, there are many kinds of components. The question is that at the beginning, this technology was mostly used for rapid prototyping, meaning to have the component printed and in your hand, and you just to check the feasibility of the component using other technology, for instance, injection molding, casting, or whatever. But more and more, the idea is to use additive manufacturing for structural components. This is what you can see here. In fact, it's a prosthesis. It's the demonstrator that we have in one of the projects in which we are involved in. And as you can understand, the additive manufacturing technology is a very promising technology because each one of the prostheses must be suitable for one patient. And so you cannot generate a mold for each one of these patients, but using this technology, you can make adjustment. You can redesign the prosthesis according to the requirement of each one of the people. So, well, this is the demonstrator. It is a demonstrator coming from a project that we have with the PUC University. PUC means the Pontificia Universidad Católica del Perú. I spent some time there during the last 2 years, just before this wonderful coronavirus. And that was a very nice experience because I could see how this technology can really employ it for one useful demonstrator. As you can imagine, these kind of processes are much cheaper than other processes, other components generated with other kind of processes, for instance, injection molding or metallic processes or whatever. The problem is that the performance of the material is very much affected by this technology, and particularly by the adhesion of the filament, as I will show you later. So this is why the numerical analysis can be interesting to study well, the performance of this element. Well, in 3D printing for using polymers, there are mainly three kind of technologies, and these technologies are very similar. Well, at least the idea is very similar to the ones used for metallic component, for metallic additive manufacturing. The first one is the fused filament fabrication. It is very similar, the idea is very similar to the wire feeding technology used for metallic alloy. Instead of having a titanium wire, here we are using filament of polymeric material. And one interesting thing is that this filament can be also enriched with fiberglass or fiber carbon elements. Okay, so there are more and more different kind of filament with better and better performance. Okay, one of the most used filament for structural application is the ULTEM, because this kind of material is fire resistant, and this is one of the key requirements for aeronautic or automotive industry. The second kind of machine is the selective laser sintering. This is quite similar to the selective laser melting used for metals. The difference is that in case of melting used for metals, you generate a melt pool, which is moving according to the power source, while in case of laser sintering, it is just a matter of sintering, of packing the powder through the heat source. And finally, the multi-jet fusion. This is a technology owned by HP. It is similar to the selective laser sintering. Mainly, a powder is used, but instead of using a heat source like the laser, they use a binder jet, which is able to wet the part of the section of the layer that you want to sinter, and then there is an ultraviolet lamp able to solidify this layer. So in fact, it works very much like a standard printer, because you have an ink jet following the scanning sequence that is supposed to be printed. And the advantage is that the lamp is going through the full layer at once. So you don't need to follow the scanning sequence as the previous one, as the selective laser sintering, but at once there are different lamps that at once just sinter all the layer. And so typically this technology, it is 10 times faster than the previous one. The problem is that the stiffness and the strength of this component is typically not so good as the selective laser sintering technology. Okay. So in this work, I will focus the attention on the FFF technology. So it is also referred to FDM. It's a technology where, as you can see in the picture, there is a wire feeding, and typically the most advanced machine use two kinds of filament, one for the printing and another one for the supporting structure. Well, the supporting structure are needed when the angle the inclination with respect to the horizontal is higher than, is lower than 30 degrees or more or less. Okay, so and this support instruction should be easy to be eliminated, and it is so that typically these filaments are can be removed just using water, so are solvable in water. But at the end, the main question is that the printing process make the construction in a layer by layer manner, and so as you can see in these figures, it is clear that the process itself generates an anisotropy into the component just due to the fabrication process itself. Moreover, to inform the printer on which is the sequence of the printing, you need a slicer. A slicer is it's a tool able to generate all this sequence, and as you can see in these figures, one of the most used environment is Cura. This is an open source, very much used in this community. It is produced by Ultimaker, which is one of the printer. And the good news is that it's an open source, so you can add features. And what we are looking at is the possibility to add a solver, a mechanical solver, able to compute the strength of these fabricated components. Okay. I'm showing this picture not only for this, but because, as you can see, when you have a mechanical component to be printed, the software generates different kind of printing pattern. I will show you later, but the question is that here you can see different colors. Okay, the red color indicating the contour of the external boundary or the skin of the component. Then you have this one, this brown one, which is the inner structure. This can be just an infill structure, or can be a lattice structure, or well, any kind of inner structure typically used to reduce the weight of the component. And finally, there are other colors like this yellow here, which is another kind of printing pattern used typically for covers, top and bottom covers. So situation in which the orientation of the surface is as an angle lower than 30 degrees. So for almost vertical surface, the printing pattern is, let's say, it's indicated by this red color, and for almost horizontal patterns, you have this yellow color. And the slicer also used a blue color for the supporting structure. I will not talk about this. Well, so the question is, when you print component, this is an example of a component printed by IQS, or IQS in Espanol, Institut Químic de Sarriá. Okay, is one of our partners in one of the projects we have. Okay, this is a component made by Ultem for mechanical application. Okay, they just remove part of the external skin just to show you the inner structure. In this case, you have this kind of infill. Okay, this component is printed like it is. So this is the table. Okay, so this is what we call the cover. It's printed horizontally. Then you have the external skin, like this one, okay, all around. And then you have the infill. So typically, according to Cura or other kind of slicer, there are three kinds of printing partners. Okay, one is the one used for the external contour or the skin. Okay, typically are aligned filaments. So this means that all the filaments follow the same alignment or around the boundary, for instance, and they are pilled one above the others, okay, to generate the full contour. Second, for top and bottom covers, the printing is different. It's typically defined by a crossed filament pattern, 45 minus 45 degrees. So one layer is 45 degrees, the following one is minus 45 degrees, and so you have a completely different pattern. And finally, you have a pattern for infill. There are many different kind of infill structure, but the most used, let's say, the default one is this type of infill. It's also 45 minus 45 degrees, but there is a spacing between the filament, and this allows to choose the required, let's say, infill density according to the specification that the component needs. Okay. The question is that if you look at this printing pattern, you can understand that typically all of them can be treated as transversally isotropic materials. In this case, it's very obvious because you have the double crossed filament generating an almost isotropic plane aligned with the table, and then orthogonal to the table, you have a different kind of properties. So the isotropic plane is the XY plane, and the theta, the building direction, is the different one. Okay. For external contour, it's almost the same, but it is the same because all the filaments are aligned in this direction, but also they are also aligned in the building direction. So you have the same kind of adhesion in the plane and in the building direction, while the direction of the filament is the different one. So both of them are transversally isotropic, but let's say the isotropic plane is different. Okay. Finally, for the infill structure that, as I told you, is the most common default infill technology to fill in this kind of structure. Also, in this case, due to the symmetry of this infill, you can think into a transversally isotropic infill, where the XY plane is the isotropic plane, and within the building direction you have the different behavior. Okay. Well, if you consider other kind of infill structure, this can be different. So generally, it is the most orthotropic material. Well, in the different projects in which we were involved, we had the possibility to characterize experimentally the materials. And one of the ideas that we had is that the characterization, meaning the specification of the material, really depends on the printing pattern. So typically, to fulfill the constitutive tensor for an elastic analysis, you need to know the Young modulus, the Poisson ratios, and the shear modulus. For the Young modulus, it is quite easy because you just need to do tensile test, and we are using dog bone specimen. I will talk about this because it's quite important. But let's say not very standard dog bone specimen, but this shape. Okay, and you can imagine different orientation of the filament induced by the fabrication technology. So you can perform the tensile test with aligned filament or with orthogonal to the alignment of the filament, or 45 degrees. Why 45 degrees? Because here you can obtain the Young modulus of the aligned filament. like in a composite structure. Here, orthogonal to them, and we typically use the 45 degrees because the shear modulus is obtained in this kind of tensile test using this relationship. Okay? And one of the most complex stuff is to obtain the Poisson ratios, because the Poisson ratio are typically obtained measuring the contraction of the specimen. But this is quite difficult in case of plastic specimen because of the roughness of the specimen, because of, well, experimentally the results are very much unclear. So IQS decided to use the so-called digital image correlation. So they performed tensile test focusing a camera on the specimen, and this specimen is full of black points, and they follow the movement of the points to understand which are the displacement of these points in both vertical and horizontal direction, and particularly looking at this face or to the other face. Okay? So you can use this face here, or you can use this face here to check if if the material is real transversely isotropic behavior. Well, in our specific case, we have we decided to use two kinds of specimen. One to characterize the external contours, and the other one to characterize the top and bottom covers. So, in one case, the specimens are printed using aligned filament, but you have to check this alignment in all the different configurations. And for a transversally isotropic material, you just need to do few tests. In fact, typically for an orthotropic material, you need 6 tests. For a transversally isotropic material, you just need 3 of them. So we are using a situation in which the filaments are fully aligned in the direction, let's say, in this aligned with the specimen. Okay. This is this kind of specimen here. A situation in which the alignment is within the plane, and so that you are checking the strength and the stiffness orthogonal to the alignment of the filament, and then we print 45 degrees to compute the shear modulus. At the end, you have to fulfill a stiffness matrix like this. Here probably is more clear. Here you have the filament, okay? And the XY plane is the plane in which you have the filament aligned in the X direction, and the theta Y plane is the isotropic plane. Okay, so the theta Y plane is the isotropic plane, and then the X is the other direction. So you need the different kind of printing partner to fulfill the matrix. So here you have, for instance, how to compute the Young modulus for aligned filaments. So you need the stress, you need the deformation in this direction. In the isotropic plane, you need, for instance, in the theta direction or in the Y direction, the sigma and the epsilon. And you can obtain the shear modulus within the isotropic plane with the standard formula. And then you need the 45-degree specimen to obtain the shear modulus for these two components here. Okay, so this is the shear modulus in the isotropic plane. This is the shear modulus in the other plane. If we refer to the covers, as you can see here, the covers are made by crossed filaments, and well, you proceed exactly with the same kind of specimen, but printed in a different way. And in this case, the quantity tensor is a little bit different because the isotropic plane is the XY plane. So in the XY plane, you can perform this kind of test to obtain the sigma and the stresses and the deformation to compute the isotropic plane Young modulus and the corresponding Poisson ratio and so on. You can obtain the shear modulus within the plane, and then orthogonal to the isotropic plane, you can obtain the other Young modulus. Okay, so it is a quite difficult experimental work. And what we understood is that the printing pattern, first of all, is extremely important, as I will show you in the result. And secondly, also from the experimental point of view, it's important to be sure of the printing pattern, meaning that we typically use very thick specimen. Just to give you an idea, this is the double of this one, okay? So are quite big specimen because you don't want to have interferences due to the corner or to what is going on when you change the alignment of the fiber. So you really want to consider the full bulk specimen made by this kind of printing pattern. And if you typically use very thin specimen, you don't obtain this kind of result. And the material look much more orthotropic of what it is really big. Well, the results are something like this, okay? And you can see that there is quite an important difference between what you have in the contour and what you have in the cover. You have really a difference in this Young modulus, so in the stiffness of the material, and this is not due to the adhesion among filament, but is due to the number of filament that you are really considering and the printing pattern that you are considering. And as you can see, first of all, it is true that this transversally isotropic, and it is true that the two directions are quite different, as you can see from the numbers. And you can also see that the difference between cover and contour, it is important. I didn't put here any result about the strength, but if in the Young modulus you have a difference varying from 30 to 40%, in case of strength, the difference is about 200, 300%, because in this case, the adhesion really matters. There are other work in the literature. You can see one, this is a recent paper by Zhao, and where they did a similar work or what we did, and they tried to print, they printed different specimens similar to ours. In their case, they use a very much thinner specimen that I don't like very much, but in any case, they check the different printing orientation, and this is the evolution, for instance, of the Young modulus as a function of the printing angle. You can see also in this case that there is a quite big difference between one direction and the other printing direction. Okay, so it was quite a nice result from these guys. You can see the full evolution of the Young modulus as a function of the printing angle. We can obtain exactly the same, just considering the rotation, well, applying a rotation matrix to the two main orientation, 0 degrees and 90 degrees. Next step is how to take into account the infill structure. And there are typically there are two kinds of infill structure. This two kind of inner structure. The infill structure, which are structures that typically grow in the building direction, and so they do not need supporting structure because they just build vertically. Okay, and then there are the so-called lattice structure. These are examples of a lattice structure. There are many different kinds of inner structure, and I will talk to you a little bit later about the most interesting ones. But any case, in this work, we focus on the infill structure because are the most common structure to fill in a component. And as I told you, is the default in most of the printer. Here you can see the work that they are carrying out at IQS. These are all kinds of infill structure, include many of them are used for Auxetic material. I will tell you something later. And these are different kinds of lattice structure. As I told you, the problem of the lattice structure is that because of this conformal, you need supporting structure printed by a different kind of material that should be cleaned up after the printing operation. This is quite tricky. Well, how to deal with the infill structure? Well, the idea is to use an homogenization technique, and so the objective is to go from an heterogeneous infill structure to an homogeneous but anisotropic material. So we want to avoid meshing the infill itself, because this is crazy because of the number of elements required, because just the geometry of this. And we want to replace this infill structure by an equivalent homogeneous, even if anisotropic material, giving the same, an equivalent structural response. So we want to go from this heterogeneous mean to an homogeneous one. And to do this, we need to select the so-called, we have to define the so-called representative volume element, or RV. So how does it work, the homogenization technique? Well, you have to think on two different scales. One is the global scale, or the macro scale. This is the scale at the level of the components, where you typically define a displacement field and a strain field. Okay. In the hypothesis of first-order homogenization, we are assuming a constant deformation field. And then you have to consider a microscale, or the local scale of the infill itself. For instance, well, this is the one that it is used for this component. And let's say in this world, in this space, the solution is enriched by a finer solution. Some authors call it fluctuation. So we want to solve this RV to characterize the stiffness tensor of this heterogeneous material, and then to plug into the macro scale. How it works, which are the steps to follow this homogenization technique. So there are three steps. The so-called downscaling, where the information is passed from the global to the local scale. And then there is and this means that you have typically to define a strain field, in this case, a constant strain field. To fully characterize the full constructive tensors, you need to define 6 different independent strain field, typically 3 elongation and 3 distortion, packed like this. Okay. Then you solve a boundary value problem at the RV domain. We are assuming a periodic boundary condition, meaning that the fluctuation on both sides of the RV are the same. And you have also to consider the equilibrium of the traction in both faces of the RV. And you solve a problem in the volume of the RV, which is a classical elastic problem, where the loading is just the applied strain field. Okay? So you solve this problem, you obtain the stresses, and then the third step is the upscaling, meaning that you are averaging all the stresses at the RV to obtain the homogenized stress at the global scale. Because once you have the stress, all the stresses and all the strain for all the 6 configurations, you can build up the stiffness matrix. So we took advantage of an implementation of this procedure in Kratos, and I would like to thank Ricardo for his help. And we were able to characterize different kind of infill. Why? Because typically using the printer, you can select different kind of densities and even different kind of infill or even different kind of lattice structure. And the good news is that you can do all this work offline. Offline means that you can, in fact, generate a database with all the infill, all the lattice structure that you want, get it ready for the following computations. So once you have characterized the skin, once you have characterized the covers, materials, and once you have characterized all the different kinds of infill, you are ready to perform any simulation with any kind of software, which allows you the use of, let's say, orthotropic materials. Okay? Just to calibrate all this procedure, so to calibrate the result coming from the experiment, to characterize the skin and the work performed on the RV to characterize the infill, we decide to create a specimen like this. Are quite big. I don't have one with me right now, but are 15 centimeter long, okay, and 2 by 2 centimeter in the section, where, as you can see, you have part of the external contour printed using aligned filament, what I'm calling contour, and part of the external and covers. So the printing pattern is the cross 45 minus 45 degrees printing pattern. Inside you have the infill. Observe that we produce 2 different kinds of specimen, one with aligned filament, but assuming 2 different rotations. So as coming from the printer and rotated 90 degrees with 90 degrees rotation. Okay, and another kind of sample where the printing direction is this one, is the vertical direction. Okay. Why? Because then we could perform a 3-point bending test, both in the lab and numerically. And in this graph, we are comparing the stiffness of this sample, okay, according to the 3 different printing orientations. So the standard one coming from the printer, rotating 90 degrees. So this means that the specimen has been rotated, so the cover are now vertical, and the vertical orientation. Okay, and as you can see, it is very light color, but we are able to catch all the orientation for all the stiffness in all the orientation for this specimen. Then we move forward to a demonstrator. This is one of the demonstrators proposed by Eurecat. Miquel Dominguez did his thesis using this kind of demonstrator. It's quite interesting because as you can see, when you apply the load, part of the component is working under bending, and this part here is working under torsion. So it's very interesting, easy and interesting demonstrator. Also in this case, we were working using different kind of infill, 25% or 50%, and different thickness of the skin. Only one skin or two skin, so very thin skin or double skin, let's say. Okay? So the component has been printed once again according to 3 different orientation, and we check, we validate the software according to all this orientation. And once again, if you just look at the stiffness of the component, you can see, first of all, that the difference orientation matters, and secondly, that numerically we are able to obtain the required result. So the blue color here coming from Cura represent what I told you. It is the supporting structure. So this part is eliminated after printing. So obviously in the experimental loading, you don't have all this, so you eliminate it and you work with this. Okay. Once again, you can see the red color for the material characterized as contour, and the yellow color for the material characterized as cover. Okay. Next step, so you could ask me why you are doing this work. Well, the objective of the industry is to optimize typically, well, the orientation of the component into the printer, so how to rotate the CAD for the best printing, and secondly, to try to save as much as possible money and printing time. So one of the objectives could be just reduce the weight, and this can be done reducing the thickness of the external contour. The second possibility is to enhance the stiffness of the component, or you can try to maximize the strength. The strength really depends, for this kind of fabrication, on the filament adhesion. Because, as I told you, this strength really depends on the printing pattern. You need an orthotropic criterion. We start using the Hill criterion, which is an extension of the von Mises criterion for orthotropic material. But most probably, there are other interesting criteria like Tsai-Hill or Tsai-Vu, which take into account also the difference between compression and tension, strength in compression and tension. And this is the case because under compression, material work quite good, but under tension, the strength really depends on the adhesion, and this is quite bad. So these are a couple of benchmark that we did just to check the implementation of the model. These are analysis of strain localization using Hill plasticity. This is a strip. Our reference example to check strain localization is a strip under tension, and here you can see a first result where we are showing the sensitivity to the plastic orthotropy. So here you can see that the sigma y, for instance, has been reduced with respect to the reference sigma y. So this specimen has a lower strength in the direction 1. This is the same strength in the 2 directions and an increased strength. As you can see, the model is able first is sensitive to the strands. The orientation of the sliding line is sensitive to this, and we are able to localize and to get this very nice result. This is another interesting result because, as you can imagine, the contour is following the shape of the component. So the filaments are aligned to the shape of the component. So you need to be able to rotate the material axis according to the deposition of this material. So this is an example of strain localization and the sensitivity to the rotation of the material axis. So as you can see, also our slip line are rotating consequently. Also very nice result. Now I'm just show you some possible research line that we would like to explore. And I will tell you about the first one. It's very interesting. It's about Auxetic material. This, as you probably do not know, but we are using very much of this material nowadays, are very interesting material because typically when you push one material like this, when you have a load like this, typically the material tend to expand. When in case of the Auxetic material, they contract. So the definition of Auxetic material, it's a material with negative Poisson ratio, which seems quite unnatural, but in fact, you can artificially generate structures which behave like this. For instance, this kind of structure, of let's say lattice structure, when compressed, it transforms in something like this. It's contract. So this is very interesting. For instance, for all the protection. Well, I need to buy one, as you can see, but this is very much used for impact because of this characteristic. But you can also see Auxetic material in shoes. This is one example. Not only for this part of the shoe, for the rubber, but also for the external part, because this is in fact quite interesting because it accommodates on the shape of the component. So are very interesting, let's say, it is very interesting material behavior that really depends on the definition of the Auxetic structure that you could employ. Other examples are, I don't know, there are ornaments or there are textiles. Even if this one is a textile able to accommodate to the shape. So when you enlarge, when you stretch, it's also enlarged. So it's quite nice behavior. That could be interesting to be studied using this with technology that we have, so to be studied numerically. Other examples are Auxetic structures. So also in this case, it's very interesting because even the full structure that put very big structure like this, according to the loading, are able to increase their strength because of this, let's say, negative Poisson ratio. So I think that it is a world where we can explore and we can contribute. And I want to conclude my talk telling you that typically the printed components are really complex components because of the very complex printing pattern, because of the definition of the lattice structure, because typically industrial components are complex, really complex. So we are spending a lot of time to generate the meshes to simulate our component. So one of the idea is to, and particularly thinking on an industrial use of the software tool, what we need is to be able to generate the computational domain as easy as possible. So the idea comes from be able to read exactly the same information as the printer does. So the printer is informed through a file which is called G-code. There is another format that is called CLI, meaning standing for Common Layer Interface. In any case, it's a file defined by the printing, the sequence. Typically are polylines and hatches, defining where the nozzle need to go to follow the shape of each one of the section, defining the component. So this is a very complex, very long file, as you can imagine. This is an example. This is the logo of ArcelorMittal. We are working with them for metallic materials. But in any case, we use this just to test that we can first, the idea is to first generate a voxelization, meaning a fully Cartesian mesh, which can be generated in seconds, then intersect the bulk Cartesian mesh by this line, by this polyline, so according to the information of the G-code. So let's say activate the voxel intersected by the G-code, so you obtain a voxelization of your geometry in seconds. So this is very, very fast and independently on the complexity of the component. And the next step is to be able to coarsen the mesh. And to do this, the easiest and the fastest option is to use octave type coarsening. And this is something that is very much more and more used for structural analysis. And we have example in FEMPAR, in FEMUS, and I don't know if in Kratos. So this is one of the best way of reducing the number of elements a priori, and to have a computational mesh of a size which can be affordable for computation. And the user typically do not need to do nothing. So just reading the G-code, and this is the final result. So this is a test that the Git boys did for me. And as you can see, it's quite nice. And we are ready to launch this analysis. The next step is to assign the corresponding material to the corresponding voxel. So meaning we are thinking about receiving three kinds of G-code, one for the cover, one for the contour, and one for the infill. And according to the material characterization that we did, we are able to approach very complex geometry. The final step could be, it is not really necessary, but from could be to use embedded technology just to recover the boundaries. And this is also a technology quite well explored and implemented in many software here at CIMNE. So this could be the final step of the generation of the computational domain for additive manufacturing. So here you can see a very complex, well, a quite complex geometry that could represent one RAV of a lattice structure, the mesh generated through a voxelization, the following coarsening, and finally the embedded technology to recover the boundaries. So I think this is the way to approach the simulation of this complex part and to plug our solver into the Cura slicer and get this available to the AM community. So I want to conclude with some concluding remark here. We approach the simulation of polymer additive manufacturing manufactured component using both orthotropic elasticity and plasticity. We did a lot of work of characterization thanks to the help of our partner in different projects. And so we were able to characterize different material, both elastic constant and strength in all the directions. So we have the data to feed our models. We were able to replace the lattice structure using this equivalent homogenized material. We really could demonstrate experimentally and numerically that the printing partners really matter. So there is an important difference on the stiffness and much more on the strength, about 200–300% of difference. The numerical results are quite accurate. We are working to move forward to include the plastic behavior and so the failure of this component through the plastic model that we have implemented. The bottleneck is the definition of the computational domain, and I show you how to save this bottleneck through voxelization, octree-based coarsening, and embedded formulation, which will be hopefully the future. Just to conclude, these are the projects in which we have been involved. This is the project that we are sharing with the Pontificia Università in Peru. It is the one about the end prosthesis. Very interesting, and I would like to thank my friends in Peru for this opportunity. These are two projects founded by Action here in Catalonia, where we had the possibility to know many different partners to help us in this work. And these two projects are going to finish in the next month. But this is a new project where we have the possibility to export this solver to the market. So it is the so-called Producta. It's a project where we want to integrate our solver into Cura for exploitation into the market. And this is a still active European project where our framework is the numerical simulation of additive manufacturing component by FFF. So this is a still ongoing project. We have time to go further and to show very, very nice results. We have a couple of publications ongoing on EM and a couple of publications on strain localization using field orthotropic elastoplasticity. And finally, I would like to acknowledge partners in the project. Veiettate Eurecat for their work on the definition of demonstrator and experimental assessment. Fundación CIMNE also very much working on the printing. From Fundación CIMNE, one of the spin-off of Fundación CIMNE is Barcelona BCN 3D, which is one of the most sold printer for FFF component. IQS, I told you, they did most of the experiment for the characterization of the material, the 3-point bending, the tensile test, and so on. HP, Alstom is one of our biggest industrial partner. They are starting to explore the possibility of using additive manufacturing for many components in their train fabrication and so on, and the Hook University. So thank you very much to be here, and I hope you like the presentation. If you have any question,
Thank you very much, Michele, for the talk. It was very nice and very clear. So yeah, we have time for, short time for some questions if anybody wants to ask. I had actually one question, Michele. well, a couple of questions, in fact. You said that you, well, in the multi-scale, let's say, approach to characterize the infill, you can calculate offline, but I didn't understand properly. Did you say that you calculate, like, let's say, or you store the stiffness matrix for each infill material, let's say, and then you use it on the macro scale? Is it like this, or?
Yes, you can do like this, yes. There are complex infill, like this one. This is an ONA type infill that you can also, in this case, you can characterize offline. Then the question is just to know which is the position of this infill in the when you are performing the mechanical analysis. Okay, so the question is just to rotate the stiffness matrix according to the loading condition. Okay, typically the parts are like this. Okay? As you can see, you have a skin, you have an infill. This part is printed like this. So these are the filaments which are following the contour, and then you have an infill to reduce the weight of this component. One important stuff is that instead of using a classical infill like this, you can use Auxetic material, and this generates also an important contribution, an important improvement on the performance of the component. I didn't told you about all the previous steps we did, because, for instance, we were working with the specimen like this, where you have an infill and then you have a boundary. But this kind of mixed specimen were not very much interesting, because it was not so easy to choose between, to understand how much was the influence of the infill with respect to the contour. And so we decide to, what I show you is the last step. So effectively, different printing partner, different experiments, different infill, different experiment, and so on. So we split all the printing partner, and then we assemble into the software to perform the simulation. And this work, and the results are quite accurate.
Okay, nice. Is there any other question? Well, I have another curiosity. This is more. You talked about a demonstrator called door handle, and I imagine what it is, but I didn't understand what is the test exactly. I mean, what do you do in that test?
And you have one part of the door handle is clamped, the other one is subjected to both torsion and bending. So you have, let's say, a complex loading condition, and we want to check that our software is able to reproduce the response of this component. So nothing special. It is just a demonstrator. Nothing. It's a demonstrator.
Okay.
It's one of the demonstrator of the project. We have more complex demonstrator, but the more complex is the demonstrator, the more difficult is to interpret the result.
Yeah, I understand.
This is a quite easy one that you can even do it manually.
Yeah, I understand.
It's almost analytic.
Thanks. Okay. So, is there any other question?
Ignacia, this is Eugenio here. I would like to thank Michele for this nice presentation. And I would like to thank you and Joan for organizing this another successful webinar. I think we have been over 40 people in the audience.
Yeah.
So this is almost beyond the capacity of our physical room in Barcelona. So, and I thank all the participants. I can see people that I don't know. Maybe some of them are new researchers at CIMNE. It's a pity that we cannot meet in person. But I just want to express my thanks to everybody for contributing to these seminars with the presence, and looking forward to the next one. Thank you.